on uncertainty. In this lecture, we're going to demonstrate sensitivity analysis with 3 parameters. The example will be a retirement savings plan. And the parameters are going to be the real interest rate, the real salary growth rate, and the number of years in the plan. This is a fairly detailed set of related examples, and we recommend that you have the printouts for this particular lecture. Our goal will be to accumulate $1 million for retirement in constant dollars. If we were to accumulate $1 million in actual dollars by the time we retire, that really wouldn't be enough, I think, for most of us. So we're going to set the goal to be $1 million in constant dollars. Method 1 for saving towards that goal is to deposit the same amount each year in constant dollars. We'll vary the assumptions about the real interest rates. In all of the examples in this particular lecture, we'll hold general inflation to be 3%. So that's throughout all of the examples in this lecture. So here's a graphical representation of the savings plan for Method 1. Constant series of savings for a rather long time period, perhaps 30 or 40 years, and the goal is to accumulate $1 million. We'll let the real growth rate be 3%. G is our earnings growth rate, and in this example we'll let that be 0 for the time being. And we also have an inflation rate of 3% that's going to be sitting behind all of these analyses. So the relationship then is F is $1 million. What does the annual deposit have to be using a real growth rate of 3%, and let's say 30 years for the savings plan. When we work through those numbers, we look up the sinking fund factor, and we find out that we need to save about $21,000 per year. Well, that's probably not feasible for most of us. Let's look at another scenario. Again, Method 1, putting in constant dollars, an even series of constant dollars. But now we're going to assume that a real growth rate of 8% would be obtained. That may be an optimistic scenario. So using 8% with a sinking fund factor for 30 years, turns out we need to save $8,827 per year. Again, that's probably not feasible for someone just starting a career. Well, let's go to Method 2, a different way of depositing. Let's start out with something more modest. Let's say $5,000 per year. That may sound like a lot, but I think most of you who are engaged in professional careers or about to start in professional careers can save $5,000 per year. Just cut back on all of your expenses by 10%. Now, we're going to assume that we're going to increase this amount according to a real growth in salary. Our salary, we would hope, is going to grow faster than inflation based on increased job responsibility. Now let's say the real interest rate is going to be at least 3% per year above inflation. Using our fundamental relationship then, this is the real interest rate factor, and that's based on the market interest rate factor divided by the inflation factor. So let's look at some numbers. We'll use a real interest rate of 3%. For this particular example, we'll set the salary growth rate in real terms to be 0. We're going to work in constant dollars. We're going to start with a $5,000 savings plan. So then we accumulate using our series accumulation factor, 3% for 30 years, and we get $237,877. That's in constant dollars. That's the accumulated value. Well, that's roughly 1/4 of our goal. That's not enough. Notice that we're saving roughly 1/4 of the amount as with Method 1 and the same growth rate. We might consider this to be a pessimistic scenario. Let's look at a different scenario. But before that, let's look at how we would actually analyze this using a table or a spreadsheet. What we have in the first column is we have our deposit series. This is in constant dollars, $5,000 per year in constant dollars. Inflation factor is 3%, so the first year we're going to deposit $5,150. The second year we take the $5,000 multiplied by 1.03 to the second power. That gives us a deposit of 5,305. And so on until the last year we're going to be depositing 12,136. This factor, of course, is 1.03 raised to the 30th power. Let's see what's going to happen in the savings plan. That's shown by these columns. Our interest factor is given in this column. Remember, our real interest rate is 3%. We said inflation rate is 3%. So compounding those two together using our fundamental relationship for inflation gives us our market interest rate of 1.0609. And then, of course, that applies to the next to the last deposit. That's in there for 1 year. So the next to the last deposit of 11,783 then grows 6.09%, gives us a value at their horizon of 12,500. The very last deposit, of course, isn't in there any time, so it doesn't earn interest. The very first deposit, the 5,150, would then be worth, using this growth factor, that's 1.0609 to the 29th power. That would then be 28,600 after 30 years. This last column then is the value at the horizon of each of the separate actual dollar deposits. Take this deposit, that becomes worth this much after 30 years. This deposit becomes worth this much after 30 years. We sum those and we get a total of 577,390. That's actual dollars. So if you're able to see this in color, then the blue color represents constant dollars, and the dark red or brown color represents actual dollars. The black columns represent the inflation factors and the interest factors. That, of course, is not enough, because we take these actual dollars, pull out the inflation effect. Inflation is 3%, 30 years. That's only $237,000, $238,000 in constant dollars. But that's how you would actually do the analysis using a table or a spreadsheet. Well, let's look at a different scenario. Let's assume that the real interest rate, the real growth rate on our investments is 6%. And let's assume we're getting salary increases over and above inflation, specifically 2% over and above inflation. Then we have to use a geometric growth factor if we want to solve this problem or do the computations with formulas. This is the formula for the geometric growth factor. The very first year, we're going to be saving in constant dollars, not 5,000, but 5,100, because we're getting a real salary increase of 2% that's over and above inflation. So the A1 that is needed for the geometric growth factor is 5,100. We apply that geometric factor to get the present worth. It's the time zero value of 87,286. That's in constant dollars. So the 5,100 is growing. It's growing at 2%. Our real interest rate is growing. Our investments are growing at 6%. So then the present worth of all of those deposits is measured in constant dollars. We can find the future value of that, use the real interest rate, 6%. We get a future value, future accumulation of a little more than $500,000. And again, that's in constant dollars. We can convert that to actual dollars. We take this constant dollar amount, we apply the inflation factor, that's 3% over 30 years. This is the constant dollar accumulation after 30 years. So we have to apply this factor to the 30th power. And then we get the accumulation in actual dollars, 1,216,900. And this may be a most likely scenario. Let's look at the table for that. In the first column, again in blue, if you're seeing this in color, we have the deposit series in constant dollars. We're getting a real salary increase of 2% per year over and above inflation, so this is growing correspondingly. We apply the inflation factors, and then this is going to give us the amounts in actual dollars. So actually we're going to deposit $5,253 at the end of the first year, actually $5,519 at the end of the second year. In the last year, it'll be close to $22,000. Now we apply the interest factors, next column here. This interest factor, of course, is based on the real growth rate of 6% plus the inflation rate of 3%, so it's a little more than 9%, 9.18%. And of course, it's easy to see that because the 29th deposit is in there for just one time period. The last deposit, of course, is in there not enough time to accumulate anything. The very first deposit of $5,253 is in there for 29 time periods. You apply this 1.0918 factor to that. That's going to grow by the end of the 30 years to $67,074. That's the first deposit. The second deposit, $5,202 in constant dollars, would be $5,519 in actual dollars. After 30 years, that's going to be worth $64,543. We then sum the last column to give us our actual dollar accumulation, $1,216,019, $900. And of course, we can convert that back to constant dollars. This is the actual dollar accumulation at time 30. What is it worth in constant dollars? Apply the inflation factor with a negative exponent, minus 30, to get the constant dollar amount a little more than $500,000. And now let's look at an optimistic scenario where we take a real growth rate of 8%. That's 8% over and above inflation, and our salary is going to grow 5% over and above inflation. Now, many of you will be in industries or jobs where you're going to get even more than that. But I think for a typical professional, this might be an optimistic scenario. We're going to work in constant dollars again, using the geometric series formula. Now, the A1 is 5,250 because it's started out at 5,000. If we didn't have any salary growth rate of over and above inflation, we're getting 5% over and above inflation salary growth. So we're going to put in 5,250 in constant dollars in the first year. The constant dollar present worth of this series is 99,837. And that's worth $1 million in constant dollars. We take the 99,837. Our real interest rate, our real earnings rate on our investments is assumed to be 8%. Factor that up for 30 years. That gives us a little more than $1 million in constant dollar accumulation. When we apply the 3% inflation factor, again with the exponent of 30, that's going to translate to $2,438,000 and something in actual dollars. Again, this may be optimistic for most professionals, although I'm sure that some of you will be actually able to save more than that. Well, let's look at the table method. First column again is the it's the constant dollar deposit series. The goal was to start out with 5,000 if we didn't have a salary growth rate, but our salary is growing 5% faster than inflation. So right away in the first year, 5,250. This keeps growing at 5%, this column right here. Inflation factor is 3%. Apply each term, term by term, get the actual dollar deposit. Our interest factor is based on the 8%. That's the real earnings rate on our investments we're assuming for this scenario, plus the 3% inflation. So that's a little more than 11%. And again, you see it here for the next to last deposit, which is in there for exactly one time period. So it's 11.24% is the market interest rate for this scenario. So the factor is 1.1124. And then we base our interest factors on that rate, term by term. Each one of these terms then would translate into an amount at the end of the 30 years. The first deposit, 5,408, is going to translate into $118,731 in actual dollars after 30 years. We sum that column, and we get $2,438,489,000. Then, of course, we can find out what that value is in constant dollars because it's 30 years in the future. So apply the inflation factor with a negative exponent, and then you get a little more than $1 million in constant dollars. The table method is actually a little bit easier. It takes a lot more work, but you see everything for what it is. You see the constant dollar deposit, you see the inflation factors, you convert that to actual dollars, you apply a market interest rate factor, and then you get the value that each one of these deposits translates into at the horizon, sum that up, and then you can go ahead and convert it back to a constant dollar amount. So while it looks like it's a lot more work, with spreadsheets today, it actually turns out to be easier than using the formulas. Well, let's look at a graphical representation of this particular example. What we have here on this axis are the growth rates in our real salary over and above inflation. On this axis, it's the real earnings rate. It's the earnings rate that's with inflation factored out. And then we have the surface here that shows what the constant dollar accumulation is. Of course, what we'd like to be up here, that means we'd have to have a real earnings rate of 7% or more, and a real salary growth rate of perhaps 5% or more over and above inflation. In table form, here's what we have. We looked at 3 scenarios in detail. We looked at this scenario, a real earnings rate of 3%, no salary growth over above inflation. That gave us a constant dollar accumulation of $238,000. We looked at this scenario. This perhaps is a most likely scenario where the salary growth rate was 2% over and above inflation. Our earnings rate was 6% over above inflation, and we accumulated about $500,000. That's about half of our goal. And then we looked at this optimistic scenario that's down here in the right lower corner, where the salary growth rate was about 5% over above inflation. The market interest rate was based on an 8% real growth rate and 3% inflation. So we're talking about a market rate of this 105, $1,005,000. It's really corresponding to a market rate of 11.24%. So all the values in this table are based on the constant dollar accumulation. Of course, you can convert them to actual dollars by simply taking each one of these and then applying the factor 1.03 to the 30th power. Just take each value in the table and you get your actual dollar accumulations. Well, let's see what happens when we change the parameter n. We used 30 in the previous examples. Now let's go out 40 years. After all, with medical care, we expect to live longer, we expect to be working longer, and saving for a longer time period before we do retire. Now these are again in constant dollars, but look where the peak is. We're at 2.7 million. We're approaching 3 million in constant dollar accumulation for some of these scenarios. So again, this is the earnings rate, real earnings rate on investments, 7%. Inflation is 3%. That means we need to be getting a market rate of a little bit more than 10%. That may be optimistic. You may be smart, you may be lucky, you might find that in the investment market. And we're getting, for these optimistic scenarios, salary growth rates around 5% that are over and above inflation. Again, you may be lucky. If you're in the right industry, you can get that. If you're in a declining industry, you may or may not be able to get that. Well, let's look at the table values for that. Same parameters, real salary growth rate ranging from 0 to 5%, real earnings rate ranging from 3 to 8%. And there are several combinations where we can accumulate $1 million in constant dollars or something close to it. Let's take this combination. If you don't get any salary increases except to keep up with inflation, then in order to get $1 million in 40 years, you need to have a real earnings rate of 7%, a market interest rate closer to 10.2%. Here's another combination. If your salary is only going to grow 2% over and above inflation, then you need a real earnings rate of 6%, meaning that your market rate has to be a little bit more than 9% with our 3% inflation scenario. And then you have these other combinations. These are in constant dollar accumulations You can convert to actual dollars by taking the inflation factor, 1.03, and applying the exponent 40. Remember, we're going out 40 years in this example. The point is, it is possible to save $1 million in constant dollars. You just have to make up your mind. Start out with $5,000 per year in constant dollars. As you get real salary increases, and increase that, put your money not in treasury bonds, by and large, but put them into faster growth investments. Keep some of your money in some safe investments for emergencies. So let's summarize this lecture. We went through a fairly long set of examples using sensitivity analysis with 3 parameters. We varied the real interest rate, we varied the real salary growth rate, and we varied the number of years in the plan. We only had 2 values for that. We held inflation constant at 3% in this example. If we wanted to vary inflation, then we'd have to have more tables, more charts, same type of analysis, just more of the same. Again, the major conclusion, it is possible to accumulate $1 million with compounding where this $1 million is in constant purchasing power. That would be a nice sum of money for retirement, given that you may have some other types of retirement plans, Social Security perhaps, or employer-funded plans and so forth. The actual analysis was done with spreadsheets. We did the analysis 2 ways. We did it with formulas, but then we also did it with spreadsheets. If you're going to do this on your own, we recommend you do it with spreadsheets. It takes a little bit more work. It looks like it's more work, but it's easier to track what you're doing, and it's easier to understand what the different numbers represent.